Hello everyone. Today we are going to start a new topic. The topic is extension of collaborative filtering, but specifically we will start talking on model based collaborative filtering. In this context, in today's lecture, we are going to cover UV decomposition, which is the basis of these latent factor models. Now, what are these latent factor models? So far in model based collaborative filtering, we have seen in the last class that almost all the machine learning algorithms can be used in case of collaborative filtering situation. Like in case of traditional machine learning algorithms, you have a set of training data and you have a set of test data, row wise a set of training and testing data. But in case of collaborative filtering, it is a matrix completion problem. By matrix completion problem, we mean that in a matrix some of the elements are available and some are not known. So, therefore, you are supposed to fill up those values. Okay. So, extending this idea, now latent factor models have come up. Let me tell you, so far we have covered neighborhood based collaborative filtering. In neighborhood based collaborative filtering, the idea is you make the recommendation based on the closest neighbors choices or based on the similarity of the items that you have already purchased. Okay, so those are fairly simple, and even item based recommender systems are also widely adopted in commercial setting. However, in today's scenario, these latent factor models have become very popular because they are much faster than the neighborhood based methods. So, these latent factor based models, they leverage the well known dimensionality reduction technique and fill in the missing entries. So far this dimensionality reduction technique, we have got some overview in many places while talking about the fundamentals of the various fundamental topics related to recommender system, and we are also covered a bit at the time of neighborhood based system. So, today we are going to talk little bit elaborately on this particular topic. This diagram must be familiar to you. In one of the earlier lecture, while talking about the fundamentals, I discussed it. So, once again I bring to your notice that when we try singular value decomposition, what we do? We at one go only we try extracting the hidden concepts that is there in the data set. In this particular example, we had 5 movies, and as the name indicates, both these belong to 2 different categories, and purposefully in this example, these first 4 people like these first 3 movies and second 3 people like the the next 2 movies. So, when we make the SVD and try factorizing this matrix, what was SVD that we are going to see at the next slide. M is U sigma V transpose. What is U? U is the user latent factor, and V is the item latent factors. So, these are basically the item features. Now, these item features are extracted not from the item details, rather they are extracted from the rating behavior, assuming that people like the movies with similar concepts. This has been decided. So, in this particular example, which is of course very purposefully designed, these first 4 people, based on only the first latent factor, can be understood that they have similar choices. Similarly, the second 3, from the second component, you can know that they are they choose the second genre of the movie. So, now individually, this is the first person's detail, this is the second person, this is the third person, this is the fourth person, and so on. So, from this person likes the first concept, that is the genre here, second person the first concept, and so on. But when I move ahead, we see that the next 3 people like the second concept. So, this matrix U connects the people to concepts. So, similarly, this is your, this data is for this, these are the latent factors for the movies. So, this is the first movie, second movie, third movie. I am making this because this is the transpose. This is the third movie, this is the this is the fourth movie, and this is the fifth movie. Now, here look at this. Here all these movies, this first 3, this particular factor, this is factor 1, this is factor 2. This first factor is becoming important. For next 3 movies, the second factor, the second factor is important in case of first category movie, and this is for the second category of movie. So, this matrix view V also relates the movies to concepts. So, using these latent factor models at one go, we can extract both item features and user features, latent features. So, let us understand what was this singular value decomposition. Here we are decomposing matrix M into U sigma and V transpose, where sigma is the set of singular values. And we also understood that U is a matrix which is column orthonormal and V is also column orthonormal, and sigma is a diagonal matrix where the diagonal elements are the singular values of M. Now, we also understood that we can mathematically find out what is U, V and sigma. It turns out that U and sigma can be found out from M transpose and M transpose M. So, this is the eigenvector of M transpose, and these are the eigen values, eigenvector of M transpose M, eigenvalues of M transpose M. And we, though mathematically it was looking very nice, while computing it may become little cumbersome, because when the matrix becomes very large, finding these eigenvalues and eigenvectors will be difficult. To remind you, how did we discover these eigenvalues and eigenvectors? For eigenvalues, we constructed the characteristics equation. Then from the characteristics equation, we found out the eigenvalues. From eigenvalues, we found out the eigenvectors. And there are certain iterative method as well using power iteration. So, however, these are only possible when this matrix M is full. Besides, if we drop this orthonormality assumption, Then this u sigma v, we can think of this as u some sigma to the power half, then sigma to the power half and v transpose, and this we can call our u nu and v nu, or we have some new u matrix and new v matrix which are decomposing the original matrix M, but without this orthonormality assumption. To remind you, what is orthonormality assumption? If we take any two columns of the matrix, then if we multiply, then it becomes 0. So, they are perpendicular to each other. So, they are orthogonal as well as if we they are unit vectors as well. Now, we have this problem. The problem in this is, so far in our discussion we know that matrix M was a full matrix. Therefore, there was no computational inconvenience observed while even determining this using such formula or through power iteration. So, now we have a situation here. In this matrix M, this value is missing and this value is missing. So, in these circumstances, how do I get UV decomposition? Of course, the formula that we saw that we cannot use. So, what are we going to do? We are going to adopt some machine learning algorithm, which will be some learning algorithm, which will be simply looking at the available entries and try to minimize the error with respect to the available entries. And because of this process, the values which are missing will also keep getting updated. So, how do we proceed about it? We have to first pre-process this matrix M. Okay. Then this of course depends on the situation. So, if it is necessary you do it, otherwise it is not, and we have already discussed why pre-processing is necessary, why normalization has to happen. So, those things if necessary you do. Then you have to initialize matrix U and V. When you initialize, you can randomize the values. Then you have to start the optimization and you find out certain criteria to end the optimization process. Now, let us look at why you should try pre-processing the matrix M. So, in a typical rating matrix, of course, the method that we are going to study, it is not related to rating matrix only. This matrix M can be any incomplete matrix, and through UV decomposition you can think of completing it. So, it is a matrix completion problem. So, in particular when this matrix M is a rating matrix, then what kind of situation happen to this matrix that normalization becomes necessary. So, many times when you get the values to rating matrix, you restrict the users to give very high, low values, etc. Rather, you provide them with certain discrete values. Most of the time these values will be discrete. So, you give them a rating scale 4 star, 3 star, 1 star, some star rating you allow, thumbs up, thumbs down, such kind of things you allow. So, if the values are not distorted, there is no chance of getting an outlier. So, what kind of pre-processing is necessary? Matrix will be within the range of the data that you are expecting it to be. However, there is some situation here. What is the situation? Situation is there can be bias from the user side or from the item side. So, what is this bias? Now, look at the concept of user bias. We are going to discuss about this user bias many more times as well. but here I am just trying to introduce it. So, what is user bias? As an user, when you try giving rating all the time, your rating may not be consistent as your thought process. For example, suppose you are not very happy today and you are watching a movie. Probably you will give a bad rating, and somehow you are otherwise happy and you are watching a movie. So, even if the movie is not a great movie, you can, because your mood is elevated, you will be giving a better value. So, such kind of biases are possible. So, similarly, this bias, this is just one example, depending on place, depending on time, their bias can be always there. So, similarly, there can be bias related to the item. So, what is this bias? So, sometimes you see that some items are very highly rated. So, even you personally feel that that item is not a very good item, because others, everybody else is telling that item is a good item, probably you will try giving a better value. And many times this fact is exploited by the attackers of the recommender system. So, what do? They use many fake ratings using some fake reviewers just to escalate the rating. So, as a result, even if the movie is not so good, because of this fake ratings, suddenly the average rating increase, and if the average rating increase, a genuine user, genuine viewer becomes little biased. Anyway, so whatever may be the case, so there can be many methods to remove this user and item bias. So, first of all, we can subtract from each entry the average rating of user I followed by average entry of item I in that particular. So, when we have certain rating M I j, it is a part of the ith row and jth column may be. So, what is ith row? Ith row is for user, jth row is for the item. So, with respect to this user, there will be certain, this user must have rated many items. So, there will be some average value, let us call it m I bar maybe. With respect to him, there can be some average value, let us say m j bar maybe. Okay. Now, combining while pre-processing this, you may subtract this first, subtract my second, this one, or you may think of subtracting this first and this one second. So, in the process, the rating value may get modified, and you can even think of adding these two and subtracting from because you will be iteratively doing this. It may so happen if you follow any of these methods, it may not give consistent result, but it is okay. Now, next comes initializing u and v. As such, there is no rule for initializing u and v. Why we have to initialize u and v? Come back to your original problem. We cannot really determine, there are blank entries. So, there are blank entries. So, we cannot determine. So, therefore, we have to start with certain random value and keep on updating it as we go ahead. So, what kind of random value you will be filling up here? In general, you can put any random value, but in general it is a good choice that all these values have the same value, and many times sometimes you give the average rating of the entire matrix M, and if you have already normalized M, then probably you will be getting all these initial values to be 0. but this with this particular example that we are doing for this particular matrix. So, let us just randomly initialize this U matrix and V matrix, and after multiplying you get this one, but this one is not same as that of your original matrix M. So, where is the difference? So, you can now find the difference. So, how do we find the difference? Element wise you will be finding the difference. So, this first element 5, and what was the value? Value was 2, 5 minus 2, 2 minus 2 and so on. So, you will be finding the difference. So, next task is you are supposed to optimize this value, and you will be following certain optimization procedure, so that this U and V, which you initially have chosen as certain random values, should be slowly updating, and the error will keep on getting minimized slowly. So, to start with, we can choose any random element. So, let us choose this random element x. So, let us say this particular value we would like to update. So, if you would like to update this particular value and try replace it with certain x, and the value of x we are supposed to find, multiply these two, and the resulting matrix is this one. So, when the resulting matrix is this one, what do we do next? This is the resulting matrix. This was the original that I was telling you. This is your original rating matrix, and as I told you you randomized it with this ones and you got this 2, and you subtracted element wise 5 minus 2, then 2 minus 2, then 4 minus 2, then 4 minus 2 again, then 3 minus 2. So, if we take element wise, subtract the values element wise and take the square and add them together, you get this root mean square error. So, from this root mean square error, our aim is to keep on reducing this error as much as possible. So, what has to be done? We have to now replace it with x, and once we replace it x, this is our new matrix. Now, what is the value of x? Value of x is that which minimizes the error function. Now, what is the error function here? The error function here is element wise element you will be subtracting and taking the square. So, for the first row, 5 minus x plus 1, 2 minus x plus 1 and so on. So, you did it. Along with this, you will be subtracting others as well. So, others, on this was the first row. So, others will be 7 plus 6 plus 23 plus 21 etc. Anyway, so now from this function, how do I get this value? This value I will be getting using first order condition, which means I will be taking, let us say this function is error function, I will be taking the error function is, let us say this RMSE is function of x. So, I will be taking dfx by dx and set it to 0. Okay. So, you can try. If you take this function, you take with respect to fx. So, what will happen? So, first term 2 into 5 minus x plus 1, then this is only x. So, that is minus 1 and so on. So, this I am not going to do it for you. You do it and find out the value of x turns out to be this, and this x you now replace here. So, this x was determined from where? From solving this optimization problem, you replace it here. So, after you replace it here, then you keep on multiplying and get this updated value. So, once we have this updated value, then what next? This is not the true minimum, our aim is to still reduce further. How do I reduce? Choose another value. So, particularly just for the demonstration purpose, let us choose this value to be updated, something from the V vector, V transpose vector. So, accordingly when you multiply, here some row was getting affected, here some column is getting affected, column is getting affected. This column is getting affected. Okay. Then accordingly you construct certain RMSE which becomes a function of y, and again you use first order condition, which means you differentiate with respect to y and get the value of y. Once you get the value of y, you replace it. So, one iteration, next iteration is over, then you choose another. So, this way you can proceed. So, what is that generic procedure that you must follow? So, to choose any arbitrary element which can be either x or y, we are supposed to minimize the error in each iteration. So, this is the process to do so. To start with, we started with one element x. So, what was this element? This element was one element which belongs to rth row and sth column. So, in this particular example, what is r, what is s? R is 1, s is also 1. So, rth first row, first column. So, in my original matrix, let us say this particular value is m certain rs. Okay. So, let us do it now. To get these elements, these values, what you have to do? This row with this column, this column, this column, you have to multiply to get it. Okay. So, that is what is being done here. So, first you multiply, so which means individual element whatever was there into x and corresponding v value you are getting. Now, from m, of course, here we have used symbols rj. So, from m rj you subtract this p rj. What is p rj? P rj is this. So, square of that turns out to be this. So, this p rj is computed here. So, as a result, this becomes your error with respect to the, this becomes error with respect to the first term. Now, if this error has occurred in this entire row, so we have added them all. Remaining values we do not have to be thinking about, because they will become constant. So, when you take the differentiation, they will anyway automatically go. So, you take the differentiation, set it to 0. So, when you set it to 0, then move x to this side and you get this formula. So, this is the error update formula for x. So, similarly, moving ahead, you can choose any value y and develop one such error update formula. And using this x and y, you can iterate. You can iterate taking, see, once you took x here, second time you took y here, next time you choose some x here, some y here. So, you can in a some either in a systematic order or in some random order, you change and you update. But remember, at one go you are not going to make it quite close to the original matrix. I mean, of course, the available entries of the original matrix. So, how many times you will be iterating? It depends the error limit that you keep. So, you keep on updating, and at some point of time you meet whatever is the target epsilon difference you have decided, and you stop. And here is one interesting fact. In fact, from the very first lecture I have been talking about this Netflix challenge. In fact, all these matrix factorization based approaches which are responsible for building this model based, specifically latent factor based models have started from this Netflix challenge, and because it was a very important driver, I thought of mentioning it once again. Thank you. These are my references, and today's lecture specifically is from this one. So, we wind up and stop now. So, these are my concluding remarks. Singular value decomposition can identify latent features both for users and items in one go. UV decomposition simplifies SVD and violates orthonormality assumption. So, UV matrix can be viewed as latent factor matrices for users and items respectively. Now, when matrix M is not fully specified, some of the entries are blank, UV can be computed by minimizing the error with respect to specific entries in M. With this process, missing entries in M can be computed at one go. So, this can be treated as a matrix completion problem, and we have to learn the value of U and V. With this, we wind up this lecture. Thank you.